Section 3, GPU computing systems with PCIe adapters. It's about 1 decade ago that Nvidia briefly started the GPU computing with GPUs in the form factor of PCIe adapters. Even today, you can still buy servers with GPUs in the form factor of PCIe adapters to do your GPU computing. For these kind of systems, there is very clear architectural fact is that the CPU and the GPU are linked by PCIe. Now we should see it this way. The GPUs are hooked to the servers by using the PCIe link here. Now you can have multiple GPUs per server. They are hooked to the servers by using these PCIe links. Okay, or sometimes you need to have PCIe switches, etc., etc. It doesn't matter. This is the fact. Now, there is an architectural fact is that the CPU and the GPU, they are not symmetric. That means what? That means we take this CPU, for example, the CPU can access its memory. There is no problem. Now, we should say it this way, the CPU can access the host memory. The GPU are hooked to the server. The GPU can access the GPU memory. There is no problem with that. The CPU can access the GPU memory. There is also no problem. The problem is that the GPU cannot access the CPU memory. This is not okay. Not okay. Not okay. So this is a kind of a symmetric situation. CPU can access GPU memory, the GPU cannot access CPU memory. I won't explain here why it's like that. You just take it for granted for the moment. In section 5, we are going to have a look at the Grace-Hopper superchip. For the Grace-Hopper superchip, the CPU and the GPU, they can access each other's memory. That's going to be a symmetric situation. And then after you have understood how it works, and then you can understand why it doesn't work here. But for the moment, you take it for granted. The other fact is that the GPU is connected to the CPU by PCIe link, and then you have a bottleneck here, which is the PCIe link. This is a picture I put from the internet. I have noted here where comes this picture. This is a copyright. The copyright goes to owner of this web page. Okay, I just put this picture. And the link between this CPU and the GPU, the PCIe link, we have the bandwidth, which is 8 gigabytes per second. If you look at the memory bandwidth, this IMC, I suppose that means Intel memory controller. Okay, I'm not 100% sure. Let's just take it for granted it's Intel memory controller, it doesn't matter. The memory bandwidth is 30 gigabytes per second for the server, for the CPU. And for the GPU, we have 150 gigabytes per second, which is the bandwidth for the GPU memory. That's the early stage of the GPU computing because we have noted that this PCIe version is version 2.0. Okay. With the evolution of the technology right now, we have the PCIe with version 4 or 5. For PCIe version 4, we have the PCIe link bandwidth, which is 32 gigabytes per second, single direction. And for PCIe 5, that's 64 gigabytes per second, single direction. But if we have a look at this memory bandwidth, the CPU part, suppose we are using the Turing CPU from AMD, we know that the memory bandwidth is 614 gigabytes per second per socket. So if you are using servers with 2 sockets, you have to multiply by 2. And then we have a look at this Hopper 2 GPU. If you are using Hopper 2 GPU, we know that the memory bandwidth is going to be 4,800 gigabytes per second. Wow, that's a lot compared with PCIe. So here, clearly from these two pictures, we know that there is an architectural bottleneck between the CPU and the GPU. The communication between the CPU and the GPU, or we say it the other way, the communication between the server and the GPU, because the GPU is hooked to the server by PCIe. The communication between the two has to go through this bottleneck of PCIe. This is the architectural fact of this generation of GPU computing systems with GPUs in the form factor of PCIe adapters. Okay, but anyway, Nvidia has made it work. It has to work. Now, how does it work? If you look at this kind of program, the GPU computing program, which use this kind of GPUs in the form factor of PCIe adapters. Basically, you can separate the code into two parts. One part of the code, which is going to be running on the CPU or on the host. This host part, this part of the code, they need to do their computing if they have to. And then besides that, they have to do these tasks. And these tasks is something they are doing for the GPU because they are going to initialize the heap runtime and select the GPU. And a heap is a heterogeneous interface for programming. So that's the programming tool, the programming model of AMD for GPUs. That's very similar to the CUDA programming environment, to the CUDA programming model, to the CUDA programming tool. So, but here I just used AMD as an example. So here is marked a heap runtime. And the host code also need to do this date preparation. The date preparation really means that you need to transfer the data from the host to the device, to the GPU. Why? As I said, that the GPU cannot access the host memory. If you want the GPU to work on piece of data, it cannot access the data. It cannot work on it. So you have to make the transfer of the data. That means you need to prepare the data for the GPU. And then you need to call the kernel function call on the GPU to launch the execution of the kernel. And this is the responsibility of the CPU. It's going to help the GPU to do that. And then the CPU also need to do the synchronization. If you have, for example, if you have multiple GPUs in your server, you need to synchronize. You need to do the synchronization. And if the GPU reports an error, it's the responsibility of the CPU to do the error handling. At the end of the day, it's the responsibility of the CPU to clean up the things and do the resource management. Now, most importantly, that the CPU need to copy the data back from the GPU to the CPU, because this is the place you need to have the data in. So this is, if you have a piece of code, a GPU computing code, the CPU part, the host part of the code, they need to do all these tasks. And then what's going to be the tasks for the GPUs to do? Okay, the GPUs, what they need to do, they need to do thread grouping. They need to do thread indexing. They need to do computation. Now, that's for sure, because that's the purpose. That's what we want the GPU to do. And the GPU need to synchronize its threads. Okay, just to point out that here, we have just mentioned that we have a kind of architectural bottleneck between the CPU and the GPU, which is the PCIe link. So that means for each data transfer, you need to make this transfer worth it because you need to pay the overhead. So you need to make the GPU fast enough. You need to make the GPU to do the computation fast enough to make your overhead of transferring the data worth it. Otherwise, you are going to be wasting your time, wasting the host time. So that won't make things reasonable. That doesn't make sense. So you have to make things really fast with GPU. And the GPU is designed to do that. We are going to find out is that for the GPU computing, the common sense is that you need to have enough threads to make this data transfer overhead worth it. So what does that mean? It means that you need to have enough threads, more threads to make it worth it. The common sense is that you need to have around 1 million threads to make the data transfer worth it. So we are going to have a look of an example, but anyway, just bear in mind that you need to have at least around 1 million threads. More threads, that's more better. More data, that's not a trouble. If you can have more threads to work on your data, to really speed up things, that's going to make your overhead worth it. So we have talked about this program, the GPU computing program using PCIe adapters. And we have discussed that this GPU computing program, which use these GPUs in the form factor of PCIe adapters, you are going to have a separation of the tasks. You are going to find out which line of the code is doing which kind of task, etc., etc. So here, I'm going to stop here. We are going to have a rest of 5 minutes, and later on, we are going to have a look at this code. We are going to go through this code line by line to understand how this GPU computing is going to be done. What's the source of the programmers when they are going to program these kind of GPU computing systems with GPUs in the form factor of adapters. Okay, so let's rest, have 5 minutes.